All right, so welcome back. We're going to get started on lesson 4.4. It's a 2-day lesson, so I'll do half the problems in this lesson, then we'll come back and do the other half of the problems to complete the lesson for the next day. All right, so let me present my screen and we'll get started. Okay, so we're going to be talking about factoring, which again is a concept that you are familiar with from Algebra 1. We also factored a little bit in geometry. So we're going to be factored by grouping. We're going to be looking at quadratic form, factored completely, different factoring patterns. So first off, factored completely. A polynomial that is written as a product of unfactorable polynomials with integer coefficients. So you can see the example here. We started with a trinomial. There is a GCF. There's a greatest common factor of 3x, so we pulled that out first. And then the trinomial that's left in parentheses can be broken down to the two binomials that multiply back to give you that trinomial, okay? And then that would be factored completely. Factoring by grouping, it's a method that we use when we're given four monomials. So when we're given a polynomial of 4 terms, we typically group the first 2 together and the last 2 together, and then we look for a GCF in the first 2, look for a GCF in the last 2, and then typically what's left over when we factor out those GCFs is a common binomial factor. So you can see the x plus 3 matches the x plus 3. That is now your GCF, so notice that gets written out front. And then when you divide this by x plus 3, you're left with the x squared, so that goes there. When you divide this by x plus 3, you're left with a 2. All right, quadratic form, an expression of the form ax squared plus bu plus c equals 0, where u is an algebraic expression. All right, so you can see an example here, 16x to the fourth minus 81 is equal to the quantity 4x squared raised to the second minus 84. All right, it says equals u squared minus 81, where u is equal to 4x squared. And I'll explain that more when we get into some examples. We have 2 patterns as well, special factoring patterns. We have a sum of cubes and the difference of cubes. Okay, so we'll see factoring patterns such as those in these examples. I wrote down the rules for factoring, kind of a step-by-step guide. The first rule, no matter what factoring problem we're looking at, we always look for a GCF first. Then we go on to count the number of terms. If there's only 2 terms, then we're going to look for a pattern such as the difference of squares or the sum of difference of cubes. If there are 3 terms, we can still look for a pattern and or just do guess and check, which is like backwards FOIL. And then if there are 4 terms, we factor by grouping. All right. Okay, so factor the polynomial completely. As I said, we're going to do half the problems tonight, so I'll stick with the left-hand column. All right, so I'll do A, C. I'll just work down this column, and then the next lesson we'll do the other column. So let me get my pen ready. All right. So the first step, as I said, is to look for a GCF. Look at the numbers, see if the coefficients have any factors in common. Oops, sorry about that. And then look for the variables. Hopefully you can see that they all share a factor of 20x in common, so that GCF goes out front. Now, technically what we're doing when we say factor it out or pull it out, you're dividing all of these by that GCF. Divide by 20x, divide by 20x, divide by 20x. So what's left over when you divide by 20x? You're left with an x squared. What's left here when you divide by a 20x? You're left with an 11x. And then what's left here when you divide by a 20x? The x's cancel completely. All right, so you're left with 600 divided by 20, which is going to give you a 30. All right, so now, and typically we do that step in our head, but I did just want to show you what we were doing when we say factor it out or pull it out. So now we have to see if that trinomial can break into 2 binomials. So the question you have to ask yourself, are there 2 numbers that multiply to a 30 and add to a negative 11? Well, if you have a negative 6 and a negative 5, that'll multiply to a positive 30, but a negative 6 plus a negative 5 adds to a negative 11. So this is your polynomial factored completely. All right. Let's keep on going. Let me scroll down a little bit. All right, the next problem. Again, you're going to look for a GCF, see if there is a GCF. 27 and 8 don't share any common factors. So scroll back up for a second. Since there are only two terms, the next thing is to look for a pattern. Is it a difference of squares or a sum or difference of cubes? Okay, so let me scroll back down. Well, it's not a difference of squares because first off, difference means subtraction. It's not even subtraction, and they're not square terms. But is it a sum of cubes? It is a sum of cubes. The first term is a perfect cube, and the last term is a perfect cube. So ask yourself what number cubed equals 27, and that's a 3. So I'm going to rewrite this as 3a to the third, right? If you have 3a to the third, that means 3a times 3a times 3a, which is 27a cubed. So it's just another way of writing 27a cubed, all right? Then I'm going to write 8b cubed as 2b cubed. Okay, so the pattern, and if you remember, I talked about SOAP, same opposite, always positive, in a previous lesson. The pattern for factoring is going to be a binomial followed by a trinomial. SOAP is for the signs. It's going to be the same sign. So since it's addition, a plus sign goes here. Then it's going to be the opposite sign and then always positive. So that's your signs. Okay, so SOAP just helps you with your signs. Now, as far as factoring, it's going to be a 3a in this spot and then a 2b over here. Then what you do is you square the 3a. So what is 3a squared? It's going to be 9a squared. Then for the middle spot, you multiply the 3a and the 2b together. So 3a times 2b is 6ab. And then you have to, oh, nope, that's it. 6ab, sorry, 6ab. And then you have to square the last term, which is 2b, and that goes in this spot here. So 2b squared is 4b squared. And that is how you factor a sum of cubes. All right, we'll do more of those patterns moving forward. Let's move on to D. All right, so for the next one, you're looking for a GCF. All right, there is no GCF besides a variable of t, so let's pull the t out. You have t cubed as the GCF. So we're left with 5t to the third plus 2t squared minus 5t minus 2. After you factor out the GCF, there are 1, 2, 3, 4 terms. So a 4-term polynomial means that you're going to try to factor by grouping. So you're going to put parentheses around the first 2 terms, 2t squared. And then you're going to put parentheses around the last 2 terms, which is negative 5t minus 2. All right, so then ask yourself, what is the GCF for the first 2 terms? There's a t squared in common, so that gets pulled out, t squared. And what's left over, when you divide this by t squared, you're left with 5t. When you divide this term by t squared, you're left with a 2. All right, what's the GCF of the next 2? I'm just going to factor out a negative 1. All right, that way my lead coefficient's positive, and you notice 5t2, 5t2, but they're different because it's different signs. But if I factor out a negative 1, then I'm left with 5t plus 2. All right, so now what's inside of your brackets? What is the GCF? What does this term, what factor does this term have in common with this term? They have a 5t plus 2 in common. So that is actually your GCF, 5t plus 2. We're going to divide this term by 5t plus 2. And you divide the first term by 5t plus 2, you're just left with a t squared. And then divide this term by 5t plus 2. When you divide out the 5t plus 2, you're just left with a negative 1. Now, it would be nice if we were done. We're actually not. I am going to drop the brackets because they're not necessary at this point. So let me rewrite it without brackets. We're actually not done. Crazy, crazy problem. We have one more step. Always look inside the parentheses and ask yourself, am I done factoring? So you look for a GCF, there is none. You ask yourself, is this a pattern? Is this a difference of squares, difference of cubes, sum of cubes? It's not. Next set of parentheses, is there a GCF? There's not. Is it a pattern? Is it a difference of perfect squares? It is. All right, and if you remember, your difference of perfect squares pattern factors into two binomials. One gets a plus, one gets a minus. It's going to be T1, T1. Okay, that's an old factoring pattern from Algebra 1. The rest of the problem just gets brought down. And you're done. So it is a kind of a crazier problem, okay? But definitely something that you should be able to handle. All right, so your final answer is t to the third times the quantity 5t plus 2 times the quantity t plus 1 times the quantity t minus 1. And if these factors are in different orders, it's absolutely fine. Okay. Where's my mouse? All right. Let's look at E. All right, so for E, look for GCF. There is none, right? They don't have y's in common. There's no numbers, no coefficients in common. So then I'm going to try to break it into two binomials, right? So y squared times y squared will give me y to the fourth. And then I have to think of factors of 48. And there's multiple. So if you need to like make a list over here, 1 times 48, 2 times 24, right? You could list them down 3 times 16, and you keep going 4 times 12, okay? So which of those factors will add or subtract or somehow combine to a negative 13? Well, if you had a negative 16 and a positive 3, wouldn't that add to a negative 13? And since we really want to multiply to a negative 48, you have a negative 16 times a positive 3, negative 16 times a positive 3. That'll multiply to a negative 48, but combine to a negative 13. All right, let me erase my factors. Okay, look inside the parentheses. Is there a GCF? No. Is it a pattern? Because it's only two terms, so I'm looking for difference of squares or difference of cubes. This is a difference of perfect squares. Both terms are perfect squares. All right, so that one binomial is going to factor again into y minus 4, y plus 4. The other binomial stays the same because there is no GCF and it doesn't follow any patterns. And that would be your answer for that one. All right, let's keep going. All right, so for F, I have 5p to the third plus 5p minus 5p squared minus 5. Okay, there's a GCF. There's a GCF of a 5. So I'm going to pull that out first. And what I'm left with is p to the third plus p minus p squared minus 1. It's a grouping problem again because there's 4 terms. So I'm going to group the first two together, p to the third plus p. And then I'm going to group the second two together, negative p squared minus 1. Look for GCF inside each set of parentheses. GCF here is a p. When I factor it out, I'm left with p squared plus 1. GCF of the next two, I'm going to factor out a negative 1. Remember, I like my lead coefficient to be positive, plus I'm noticing that if I factor out a negative 1, this will then match this, which is what I want. So factor out a negative 1, and you're left with p squared plus 1. Right, so write that GCF of a 5 down. Now what's the GCF? What does this have in common with this? It has a p squared plus 1 in common. That's your GCF. When you factor out, when you pull out the p squared plus 1, what are you left with? You're left with a p. When you factor out, pull out the p squared plus 1, sorry about that noise, you're left with a negative 1. All right, and that is the answer for that one. All right, give me 1 second. I need to check to make sure everyone is okay with that big bang. Okay, everyone's fine. Where was I? All right, so let me erase that. Moving on to K, or on to, sorry, yes, K. K is the next one we're on. All right, so I have 12 squared minus 22K minus 20. Again, first step is to look for that GCF. There is a GCF of a 2, so factor out the 2 to start. Divide this by 2, you're left with 6x squared. Divide the next term by 2, 11x. Divide the last term by 2, negative 10. All right, now I'm trying to break this trinomial into two binomials. This factoring is a little more challenging because our lead coefficient is some number other than 1. So in my first two spots, I could have a 6 and a 1. I could have a 2 and a 3. And this is where guess and check comes into play. All right, I'm going to try a 2x and a 3x. And the factors of 10, I could have a 1 and a 10, or maybe it's a 10 and a 1. I could have a 2 and a 5, or it could be a 5 and a 2. All right, let's try. I'm going to purposely do this wrong. I'm going to do a 2 there and a 5 there. Okay, so the first two terms will multiply to give me a 6x squared when I FOIL. And the last two terms will multiply to give me a 10. All right, I need a middle term of negative 11. To get that negative 11, I have to multiply my inside terms and my outside terms. That's 10x and 6x, and add them. There's no way to take a 10 and a 6 and make an 11. So that means I have to flip-flop where I put my 2 and my 5. All right, so I'm gonna have to erase all that. All right, so let me rewrite what I had. I'm gonna flip-flop my 2 and my 5. So here's my 5, here's my 2. Now when I check, when I FOIL, my outside terms give me a 4x. My inside terms give me a 15x. If I have a negative 15 and a positive 4, that'll combine to give me a negative 11. So I'm going to put a positive here and a negative there. Okay. And again, you can FOIL it all out and make sure you get the original problem. Sorry about all the background noise if it's kind of noisy, guys. All right. Let's move on to the next problem. So the next one is this the last factoring problem? Yeah, I think this is going to be the last factoring problem for this section. All right, so we have 3m squared minus 48m to the 6th. Look for the GCF first. There's a GCF of a 3m squared. If I factor that out, I'm left with 1 minus, right? Because if you divide this by 3m squared, so 1 simplifies to a 1. Erase that. Minus 48 divided by 3 is a 16. If you're pulling 2 m's out, dividing out 2 m's, you're left with m to the 4th. All right, so now you have to ask yourself, is this any factoring pattern? Because there's no GCF, but it is a difference of perfect squares. All right, and a difference of perfect squares breaks into two binomials. 1 times 1 multiplies to give me 1. 4m squared times 4m squared multiplies to give me 16m squared. 1 gets a minus, 1 gets a plus. Before you say you're done, look inside each set of parentheses. No GCF, but is this a factoring pattern? It's again a difference of perfect squares. So this one factors one more time. Two binomials. This one's going to stay the same. This one is not a pattern, okay, because it's not a difference of perfect squares. It's a sum of perfect squares, which we don't have a pattern for, a factoring pattern for. So this one factors because it's a difference of perfect squares. It's going to factor into 1 times 1, 2m times 2m. 1 gets a minus, 1 gets a plus. And now you are done factoring. All right. Okay, let's keep on moving along. We're just about done for part 1, day 1. All right, it says show that the binomial is a factor of the polynomial, then factor the function completely. All right, so I think for today we'll do, I guess we'll do two of them. All right, so you have two options here. You could use substitution or synthetic division. If you're using synthetic division, you're looking for the remainder of 0, right? So if you remember in the last lesson, we evaluated the function when given a certain value. We also use synthetic division to divide. So we know that a number is a factor of another number if it divides it evenly. For example, if I said is 2 a factor of 12, you say yes, because yes, you know that 2 times 6 equals 12, but also it's because if you take 12 and divide by 2, you get an answer of 6 with a remainder of 0, right? There is no remainder. All right, but if I said is 2 a factor of 41, the answer is no, because when you divide 41 by 2, you're left with a remainder. It doesn't go in evenly. So for these problems, it's really no different. If you're asked whether or not x plus 1 is a factor of x cubed minus 13x minus 12, you want to know, does it divide in evenly? Do I get a remainder of 0? Okay, so I'm going to show you two different options for the first problem. First off, your k value is a -1 for this first problem. K is a -1, right? Because when we divide by x minus k. So if I use synthetic division, I'm going to set up my k value, my coefficients, put in those place value holders are 1, 0, -13, -12. Drop the 1, multiply to get a -1, add to get a -1, multiply to get a +1, add to get a -12, multiply to get a +12, add to get a 0. Okay, so you can say, yes, x plus 1 is a factor of f of x equals x cubed minus 13x minus 12, because we have a remainder of 0. All right, now that's just one option. The other option is to substitute in, right? We said the k value is -1 for this problem. So if I take f of -1 and I substitute in -1 cubed minus 13 times -1 minus 12. So -1 cubed is -1. Then I'd have a +13 minus 12. -1 plus 13 is 12 minus 12, which gives you a 0. So that's another way to show that x plus 1 is a factor, because I have a remainder of 0, right? When I plug it in, it evaluates to 0. So that's another option. The third option is to factor. We're going to factor x cubed minus 13x minus 12 from synthetic division. From synthetic division. So I know I erased the synthetic division already, but when we did synthetic division, I'm going to stick it up here again real fast, just copying out of my notes. I had 1, 0, -13, -12. I dropped the 1, multiplied again, -1, -1. It's 1, that's -12, that's 12, that's 0. So when I did synthetic division, this was the quotient, right? So basically, when I divide this by x plus 1, I'm left with 1x squared, because remember, it's 1 degree less, minus 13x minus 12. All right, so that is the polynomial that you're left with. Now, when you divide it by x plus 1, that means that x plus 1 times this polynomial will give me this trinomial. And then I can break that down into x with two numbers multiply to 12 and add to a negative 13. Oops, sorry, I'm writing the wrong number down. Well, I didn't even write the right number up here. Sorry, guys, I have a copy error. Let's try this again. I don't know where my 13 came from. It's x squared minus 1x minus 12. So I'm going to have a 4, a negative 4, and a positive 3. All right, so the question is x plus 1 a factor of the function given? Well, it is, because when I factor out that polynomial, you're left with x plus 1 as one of the factors. All right, let's try another one. Again, it's really up to you how you want to do the problem. I'm going to do synthetic division to show that x minus 5 gives me a remainder of 0 to show that it is a factor. So for this problem, my k value is a positive 5. So I'm left with, or I'm going to use 2, negative 12, 6, 20, and then the constant 0 is missing. Drop the 2 to get a 10, add to get a negative 2, multiply to get a negative 10, add to get a negative 4, multiply to get a negative 20, add to get a 0, multiply to get a 0, add to get a 0. Okay, so far I showed that x minus 5 is a factor. Okay, and the directions do say, I don't think I read the directions carefully for the first problem, although we ended up doing it correctly. It says then factor the function completely. So I did do that in the last problem, but I wasn't paying attention that it was actually asking me to do that. All right, so that means that x minus 5 is a factor. The other factor is what is left over after doing synthetic division. So this is the first coefficient, and the degree is 1 less. So it's going to start with 2x cubed, because this is x to the 4th, and you have to go 1 less. So 2x cubed minus 2x squared minus 4. All right, we still have to factor it completely, though. So from here, is there a GCF? There is. There's a GCF of a 2. And I'll eventually write it out front, but for now, I'll just write it out in front of this trinomial. So when I factor out a 2, I'm left with x cubed minus x squared minus 2. I still have to see if that can factor completely by breaking it into two binomials. All right, I'm going to write this GCF out front. So I have a 2 out front, x minus 5, and then I'm seeing if I can factor further. Did I lose something? Oh, no. It's getting late and I'm getting tired, guys. I made a mistake. Not a bad mistake, just a little mistake. Back up for 1 second. Anyone catch my mistake? When I was going down in degree, right? This is 2x cubed, then negative 2x squared, then negative 4x. I forgot my x off of the tail end. All right. Sorry about that. So my GCF is not just a 2, it's a 2x. Let's factor out the 2x this time. So that's going to leave me with x squared minus x minus 2. So I was just off by 1 variable, but that's a big deal. All right, so I'm going to write that GCF out front. And then I'm trying to break this trinomial into two binomials. So x times x will multiply to give me x squared. 2 times 1 will multiply to give me a 2. In order to get a negative 1, the 2 has to be negative, the 1 has to be positive. And now I'm factored completely. So just as a quick recap, okay, and we're going to do one more problem in the next lesson. You first have to use synthetic division to find out whether or not x minus 5 is a factor. And what you're looking for is a remainder of 0. So if you get a remainder of 0, it is a factor. If it's a factor, you write that factor down. This is the factor that was given. I just wrote it here. And then what's left from synthetic division, those coefficients, are used to write your other polynomial. And then you see if that other polynomial can be factored again. The coefficients, 2, -2, -4, 0, you're going to put the variables that are 1 degree less than your dividend up top, what you're dividing into up top. So since this starts with an x to the fourth, your answer is going to start with x to the third. Okay. All right. So that is it for part 1. And we will finish up. Where are you guys? Okay, there we are. We will finish up this lesson. I'll do the other factoring problems in day 2. All right. Bye.